Hello everyone and welcome on my channel. I am Ivan Fedyanin, I am software architect and a PhD. In this series of videos, we will cover different aspects of distributed systems and software architecture. And today we start with Introduction to Consistency Models. My goal is to give very understandable and easy explanation of some complex topics. If you want to find out more information about me, just visit my website fedyanin.ai or my LinkedIn profile. And if you have any questions, any comments, maybe any doubts about topics of the lecture, don't hesitate to leave a comment or send me a message in some way, and I'll try either to answer it if I can, or I can take this into account when I'm preparing next videos about this topic. So any feedback is welcome. Our today's topic is Introduction to Consistency, and the first part of the lecture will be why we need consistency at all. And only after that we will cover different well-known consistency models such as linearizability, sequential consistency, FIFO, causal, eventual, and so on, and a glimpse for other consistency models as well. Let's start with a very simple thought experiment. We have black box storage. It's black box here because we don't care what is inside, and we just care that we can write information into that storage and we can read information from that storage. And we have Alice here. Alice is a single client of that storage, and Alice first write 1 to X to this storage, and then she reads X back. And the question which I want to pose here is what do you think she must get back? Well, obvious answer which first comes to mind that she always must get back 1 because we just wrote 1 into that storage. And it's very intuitive, but remember that we don't know the structure of the storage and it can be anything there. So let's not jump to conclusion and let's see the structure first. We assume that a black box has the following internals. So first it has two replicas, 1 and 2, and some synchronization link between them, and a balancer which distributes reads and writes here and there randomly to any replica. And then for Alice there could be two possible outcomes with such a storage. On the left, it's a positive case when Alice makes a write, the replication between replica happens, and despite that Alice reads from another replica, she reads updated value X. But on the right side there is another outcome which is rather negative. And here Alice writes 1 to replica 1, but now there is a problem with connectivity or with slowness or with some delays between replication in replica 1 and replica 2. And when Alice does the read, she reads null, despite the fact that she just wrote 1 into the X. There is another possible anomaly. Now we have a black box storage, Alice and Bob. Alice again writes 1 to X, and then Bob does 2 reads. And now the question is what will Bob get on his second read, provided that on his first read he read a proper value. And again, let's use the same internal structure of that black box storage, and let's see what could go wrong. So after Bob does the first read and gets 1, which we would expect, then his second read is from replica 2. And also, since it's negative case, we consider a scenario when replication did not happen by that time, when Bob reads from replica 2 and Bob reads null. And here it seems for Bob like he is getting value from the past, because in the present X already 1, and in the past it was null, and Bob already knows that it's 1. So it's like a time machine, and it's called non-monotonic reads. there is even more anomalies, and in this setup it's more complex. And here we have three actors here: Alice, Bob, and Eve. Alice and Bob are communicating, and Eve is eavesdropping on them. It's a very common setup for cryptography books and articles, by the way. And they are communicating by inserting messages into the database, and each of them is connected to their own replica. And there is some background synchronization between replicas happening. Alice is asking a question, "Where are you, Bob?" And Bob answers it, "I am in Brazil." And Eve is seeing their messages only on her replica number 3. And again, if there were some problem with connectivity between replica 1 and 3, it could happen that Eve would receive those messages in the reverse order. So first she would receive answer from Bob, and only second question from Alice. And it's another anomaly which is possible. So up to now, we just have seen three anomalies, and there are a lot more anomalies in distributed systems. And as a result of reviewing those three slides and three anomalies, I'd like to highlight that in distributed systems, their behavior is not always intuitive, and there are a lot of anomalies. And now the question arises, if there are so many anomalies and so many possible internal structures of the system, how a programmer should know what to expect from a storage, how to create software if storage can behave unexpectedly. Well, a possible solution could be just to disable all anomalies, create kind of ideal storage, and use it always. And it's even possible to have storage without anomalies. But such storage could be slow, for example. And what if programmer or some application developer for some specific case would not care about some specific anomalies, but if they would lead to improved performance, the developer of application could just apply some measures on application side to prevent those anomalies. And if it was the case, developer would have to research each storage before developing application based on this storage, and it would be very long process. It would require a lot of resources and a lot of money, so it's not realistic. And here consistency model comes, and the consistency model is just relieves application developer from researching deep structure of the underlying storage, because consistency model, it just provides a contract. It says in that particular storage such anomalies are possible and such anomalies are not possible, and it's defined by consistency model. And now application developer having this consistency model, he or she, they don't need to research to know the internal structure of the storage, and they just need to view this contract, this consistency model, and that's it. And there are some consistency models which are well known, and we can place them in the continuum, which is provided here on this slide. And on the far right side, there's linearizability. This consistency model, it's almost ideal. It provides almost strongest guarantees, but it's the slowest one. And on the opposite side, there is eventual consistency, which is opposite. It has weakest guarantees, and it can lead to a lot of anomalies, but it is very fast. Let's move to linearizability. The general idea of linearizability is that system operates as if there was only one storage. This model is presented on the slide, and we see one storage and three processes, A, B, and C, and they are taking turns connecting to the storage for both reads and writes. Such a system has the properties of atomicity of operations. It means that the operation can be either fully completed or fully not completed. Also, operations could be considered as though they are executed instantly between sending request and receiving response, because only one process can be connected to a storage one at a time, and it is connected until the operation fully completed. Furthermore, there is total order respecting real-time order of all operations. It means that each process see all sequence of operations in the same way. So they all share the same picture of history of events, of operations. And also if some operation in process A, for example, happened first, and then operation in process B, then in this total order, those operations will be in the same order. So real-time order of operations between processes is also preserved. It's worth noting here that in fact there is no global clock, and in fact, to be honest, we can't say for sure if operation of process A happened first or process B happened first. And the good part is that we don't need to have global clock to have linearizable systems, and there are algorithms which can achieve this. Also, another property is that completed and acknowledged operations are instantly visible to all clients. And this model, it's very easy to reason about, but it's quite slow. And just one more point to highlight, that this is just illustration. It's not how all linearizable systems are implemented. And also, it does not mean that linearizable systems can't have more than one storage. In fact, they can have multiple storages, but they must behave as though there is only single data copy, so that there are no anomalies. And before we move to formal definition of linearizability, we need to just to get some concepts about histories and what is it and what histories there are possible. Here we see process A with two operations, write and read. And in the bottom on the screen we have a written form of that history H. And it consists of start of the operation and end of the operation. Write X represents starts of operation of write by process A of variable X, and A OK means that the operation is finished and client received the response. And this history is sequential. It is sequential because first we have operation A started and finished, and only then there is another operation of process A which also starts and finishes. So such history is called sequential history. Please just don't confuse sequential history with sequentially consistent system. Those are different things. And here it's just history, which is sequential. Now we move to two processes. And as you can see, write by process A and write by process B, they are overlapping. And there is some common part, and it's not clear which one would be executed first. And now the question is what the read will return here, X or Y. On the bottom of the screen, there is a written form of that history, and this history is concurrent. It is concurrent because we see that operation for write of process A is divided in between by operation of process B, because we have step 1 A write X, step 3 A OK. It means that operation of process A is finished here, but in the middle of operation of process I there is operation of process B, and it seems on the picture like different colors are interleaving, and such history is called concurrent. And also there is a notion of just projection of a history on a specific process, and it's depicted on the right side of the slide. And we have history H for process A and history H for process B. One of them is in blue color and another is in black. And this projection is just if we extract from original history of operations of one process, either process A or process B. Okay, before that, we had a sequential history of one process and concurrent history of two processes. And now we see sequential history of two processes. So it's perfectly possible that there are multiple processes, but still they form a sequential history. And basically sequential history means that there is no overlappings of operations of different processes on each other. And in the bottom left side of the screen, it can be seen that now all operations are complete. So first we have start and end of operation of process A. Then we have start and end of operation of process B. And then we have again start and end of operation of process A. It's easily can be seen that all colors come in pairs, and such history is called sequential. And notice that projections of that sequential history on process A and process B, they are exactly the same as on previous slide for concurrent history. So basically it means that it's not, to understand whether the history is concurrent or sequential, it's not about histories of individual processes, it's how we interleave them together. We studied general idea of linearizability and we got a concept of history. And now we are ready to digest the definition, formal definition of linearizability. It's present on the screen, and I'd like to highlight several points which are important here. So first, in order to understand if the history is linearizable or not, we need to take this history and then reorder operations in such a way that several requirements are held. So first one, the resulting history must be legal. Legality of the history means that it follows sequential specification of this object. And this is illustrated in the bottom right side of the screen. We have two histories, blue one from 3 operations and red one from 3 operations. Those histories are provided for a register. It means that it's some object where we could write something and then read it back. And the legal history for register means that read see the most recent write, as shown in blue history. So we first wrote 1, then 2, and then we read 2, as we would expect from a register. And illegal history for register is in red, and here we again wrote 1, 2, but then read 1. It means that the history is illegal. If we consider another object, not a register, but for example FIFO queue, there will be another sequential specification for this object, because in the queue it's on the contrary. The first object is in the queue, the first should be out of the queue. So for each object there is some sequential specification which is just rules how the object should behave. Okay, next. For each process, history of that process in original history H and in the permutated history H prime, they must be the same. So it means that if we consider only operations of each specific process, then they should be in the same order in our history H prime. And the second requirement, it's related to real-time order of operations. So basically it means that if one operation in one process happened earlier than operation in another process, then in resulting history they should also follow the same relative order. And this is illustrated on the bottom of the screen on the left. We see subhistories of two processes, P1 and P2, and we see their interleaving in the history H prime. And we see that all of those requirements are satisfied, because if we focus only on, for example, blue operations of process 1, we will see them in exactly the same order in history H prime. And the same applies for P2 operations. Also, for example, operation OP1 of process 1, blue one, happened before operation of OP2 of yellow process. And in the resulting history, they are appearing in the same order. So that was formal definition of linearizability. And we are going to look at some examples. Given this history, what do you think? What read should return which is made by process A, X or Y? Let's see. Actually, both reads are possible in linearizable system, and both histories would be linearizable. First one is read Y, and on the right side it's possible that the same sequence of operations would return different results. Why it can happen? Remember that when we discussed general idea of linearizability, we said that all operations are instantaneous and they are executed during some moment between the request and response. And here on this slide, we use red arrows to depict exact moment of time when the operation was executed. And now it becomes clear. On the left side, we see that first process A wrote X and only then process B wrote Y. And that explains the result of the read. And also under this left picture, we see linearized history. All operations are go in pairs, so we have first operation of process A fully completed, then operation of process B is fully completed, and then operation of process A is fully completed. And it is a linearization of the original history, which was concurrent. On the right side, it's opposite situation when first was done write by process B and only then write by process A. And we see different linearized history of the same concurrent history. So what we can say from it that linearizability, it's not deterministic, and we can have some concurrent history, and we can have different versions of linearizable history. So it's not restricting all operations to only one sequence. It still gives us freedom to reorder them, but it's quite tight because we have to keep order of operations for one single process and between processes as well. Now let's check, for example, not a register, but a FIFO queue. FIFO queue, it's a queue where we first enqueue some object, then another, and during the queues, we will be receiving objects in the same order we enqueued them. So basically, first in, first out. This is concurrent history, because NQX and NQY are happening at the same time. Let's linearize it. And we again point at exact moment of time when it happened. It's just an example. It could be different linearization, but we are considering this one. So we pointed moments in time when it happened and reordered the operations such that there are always completed operations. And here is non-linearizable history for FIFO queue. I suggest you to pause the video and ensure that it's not possible to select moments when operations were executed in such a way to achieve this picture. Because actually the problem is with the dequeue operations, because we can't dequeue from a queue the same value twice if it was enqueued only once. It's not legal for the FIFO queue. Here is an example of non-linearizable history for a register. And again, you can check that no matter how we choose the moments when operations were executed, it's not possible to reorder operations in such a way that would explain those results. We have finished with linearizability, and I'd like to highlight the most important thing which should be left after all of those slides. Linearizable system behaves as though there is only one data copy. And because of this, there are almost no anomalies, and the system is very well understandable, and we know what to expect of it. Also, there is total order of all operations across all processes, and this order corresponds to real-time ordering of operations. Moreover, acknowledged write is immediately visible to all future reads, and once read sees the value, all future reads must return the same value, unless there was another write. And of course, it's very easy to reason about correctness in such a system, but we have to pay for it with latencies, which are high for both reads and writes. Let's move to sequential consistency. General idea is that now each process has its own storage, and he is able to make reads from the storage as much as it wants. So at any moment of time, it's possible that process does read, and the process now does not have to wait for its share of the shared storage because it has dedicated storage or cache. However, all writes are still going through one place, through write queue. So if a process wants to make a write, instead of directly amending storage, it sends a message to a queue, and then messages from that queue are distributed to storages of all processes. It means that all writes are delivered to all processes in the same order through the write queue. And it means that there is total order of writes and reads as well. In reality, there is no total order of reads because we don't control it, and each process can read as much as possible. But the idea is that we could imagine some equivalent history with the order of reads also the same for all processes, and it would be the outcome will be the same as in this system, which is illustrated here. Such structure means that there is real-time order between operations of each single process. So all operations of process A will be visible in all storages of all processes in the same order. The same applies for B and C. But unlike linearizable systems, there is no real-time order between operations of different processes. Here is a formal definition of sequential consistency, and it looks almost exactly the same as definition of linearizability, and there is only one small change here. Which one? What do you think? Do you remember? And the change is that there is no second requirement about mutual ordering of operations of different processes between each other. And it means that we can take subhistory of each process and just shift them one relatively to another and make a history out of them. Now watch closely the history of process P1, which is in blue here. And on the next slide, we just shifted. So we shifted this history and merged them together, interleaved them, and received H prime. Now watch history of P2. We also can shift operations of those processes in some direction, and now we get different H prime history. And all of those histories are sequentially consistent. Here is an example of sequentially consistent history. First, this image, it looks a bit strange because we see that processes C and D do reads, but processes A and B did not yet do writes. It looks strange, but only until we remember that we are able to shift histories of individual processes, and their relative order does not mean anything. So we just shift operations of process A and process B to the left, and we receive such history. And this history is sequentially consistent. Also, it's possible to imagine non-sequentially consistent history. On this picture, it's very similar to previous one, but the problem now that processes C and D, they read A and B in different order. And it means that they see writes in different order. But it's not possible because it contradicts requirement so that there is total order of writes. Total order of writes means that all processes must see the results of the writes in the same order. Because of it, this history is non-sequentially consistent. And there is another important property of sequential consistency. It's not compositional. Here we have two Q objects, QP and QQ. All objects of QP are colored with purple color. And if we look at each object separately, for example, let's look only on object P. History for this object would be sequentially consistent because we can just shift P and QY of process B to the beginning, and then it would be like we did NQY, then we NQX, and then we DQY. So it's sequentially consistent. If we look only on yellow object Q, then also we could shift operations in such a way between processes so that overall it's sequentially consistent execution. But if we combine two of them together, the resulting history will not be sequentially consistent. This happens because there is also requirement of an order of operations of single process. And those requirements of ordering, they form a circle. And it's infinite loop, and it means that we can't shift operations in such a way so that DQs are such which are shown on the screen. I suggest you to pause the video and carefully review it. That's it for sequential consistency. Let's go through summary. So there is also total order of operations as with linearizability. Again, similar to linearizability, each process operations appear in program order, but unlike linearizability, now there is no real-time relationship between operations of a different process, and they can be easily shifted one relatively to another. It's less strict to linearizability, and it gives more anomalies, but it is faster. And importantly, that it's non-compositional, because several objects which are individually sequentially consistent, when they form a system, it's not necessarily that the system would be also sequentially consistent. And with linearizability, it's not like that. If we have several linearizable systems, then when we join them together, the resulting system will also be linearizable. Next consistency model which we will study is causal consistency. The general idea of it that it's not always when we care about total order of all writes, but it's often when we care about order of some writes. And it means that it's enough to preserve only partial order. Partial order means that for some operations order is defined and for some is not. And it's easy to see with an example. Imagine that you are doing post on Facebook and another guy, probably in another country, on another end of the world is doing post on his or her timeline as well. And normally you would not care in which order your posts would appear in timeline, because first you might not even know that another guy exists and would not never see his post, but even if you saw and knew that guy, it's normally would not be important in which order your posts are ordered. On the other hand, if you wrote some comment under some post and then someone replies to your comment, then it is important that everyone who sees both comment and reply, they see them in proper order. Otherwise, it would not make sense. It would be strange and ridiculous. And that's the idea of causal consistency. Preserve order of important events which are linked by the order, and don't care about order of concurrent events for which we don't really care. And it's a very good optimization. It can be applied in multiple cases, and it improves the performance of the system while keeping some important order. The only tricky part here is how to detect operations for which we need to preserve order and for which we don't need to preserve order. This is illustrated on the picture. We have 4 processes, but for now focus only on process A. Notice that it does write A and then write C. The fact that this process did those 2 operations in that order suggests that by the time process A did write C, it knew that write A happened, because it happened in the same process. Now, it's important to highlight that we don't know for sure if those 2 writes, they are causally related. We don't know it, but we know that they can potentially be causally related because the knowledge of process A about write A by the time it wrote C. Okay, we know how to establish happens before relationship within one process, and it's easier. Now let's switch our attention to process B. Process B also does 2 operations. First it reads A and then it writes B. Again, we know that write B is potentially causally related to read A, because it happens after read A. But also notice that read A, it reads A because process A wrote A, and it means that read of process B and write of process A are causally related. And it means that write of process A is causally related to write of process B. And now we established happens before relationships between writes of different processes. So that's how it works in general. On the contrary, write C by process A and write B by process B, they are not causally related, because they both happen after write A, but there is no causal relationship between write B and write C. And because of that, such writes are concurrent. And if they are concurrent, it means that we don't care about their relative order and they can appear in any order. Let's see example of causally consistent execution. We have again 4 processes here, and only 2 of them are doing writes, process A and B. As you can see, we cannot say that there is happens before relationship between write of process A and process B. And because of this, it's perfectly fine that processes C and D read those A and B in different order, because they are concurrent and we don't have a requirement to keep an order between them. But if we add just one small read in process B before it does write B, now it establishes happen before order, and now write B becomes causally related to read A and consequently to write A. The same order of reads by processes C and D, they are not valid in causally consistent store, and thus they are causally inconsistent. Because now, since they are causally related, we care about their order. And they must appear in the same order, but it's not the case. Moving to FIFO consistency, FIFO consistency does not have a concept of a total order at all. Its general idea is that now each process has its own storage, and each process can read and write this storage without needing to coordinate it with other processes. So each process is owner of its storage. And what it is obliged to do for others is just to send asynchronous notification about writes which this process does. Because of this, there is no total order, and each process might see different picture, different interleaving of writes. But still, writes from a single process are seen by all processes in the same order because they are delivered through the same queue. So, for example, all writes of process A will arrive process C in the same order. FIFO consistency, because of this, it's very fast. Because now we just need to send notifications about our writes, and since they're asynchronous, there is no blockers for synchronization which is needed. But because of this, FIFO consistency might have a lot more anomalies than other more strict consistency models. This is an example of FIFO consistent execution. Remember that the picture is exactly the same as we considered non-causally consistent. But for FIFO consistency, it's perfectly fine because by definition, we don't care about order of writes of different processes. And because of this, we don't care if processes C and D would see writes of A and B in different order. Now we came to eventual consistency, which is the weakest of all and fastest of all. And the idea is very simple. Eventual consistency does not give us any ordering guarantees at all. So even writes of a single process can be visible by all other processes in any order. The only guarantee which this system gives us that if system stops accepting writes, then eventually all nodes of each process will receive all writes. But this requires full stop of the system, so that, or at least making it read-only. And as you can guess, for busy systems, it's not always possible to stop it. And it means that busy system can be a bit inconsistent always. And in eventual consistency, by intention, this time period is not specified after which everything will become consistent when the writes stopped. It can happen in a second, or probably in some system it could take minutes or even days. Such systems are very fast because no requirements about any ordering at all, but because of this they are very hard to reason about. And it's a challenge to developer to work with such system because a lot of logic should be placed into the application code. And it's error prone, and there could be potentially some tricky bugs which due to their concurrent nature, they could be very hard to catch. But despite of those negative sides, it's fast, and because of this, it's really used. Furthermore, there are two forms of eventual consistency, weak and strong. Usually, if we just say eventual consistency without specifying whether it is weak or strong, it means that we mean weak eventual consistency. And the difference is how this model handles conflicts. Because if we do parallel writes in different storages, we might change the same data. And when they merge together, it's possible that this merge is conflicting. And the strong eventual consistency, it says that all those conflicts on every node will be resolved in exactly the same way. It means that in the end, all nodes will be in exactly the same state. And weak eventual consistency, it says only that all nodes will receive all writes eventually, but if there are conflicts, potentially they could be resolved differently on different nodes, and thus if those nodes will be in different state. And of course, a weak form of eventual consistency is faster, but it's even harder to reason about. Eventually consistent systems, they are used for cases when we don't really care about order of events, or in cases when we mostly are doing reads and only sometimes we are doing writes. Example of such usage is a DNS system and counters of likes in social networks, for example. Because for counters of like, we don't really care in which order those likes were given. But we care about speed of such system and its performance. So far, we reviewed a spectrum of consistency models with the weakest ones on the left and with strongest ones on the right. And it might seem that it's very logical, beautiful, and there is order between all consistency models, and there is finite number of them. But reality is a bit more complex than that, and authors of the article, which is given here, they made excellent analysis and analyzed all known consistency models and ordered them in a tree depending on their strictness. And as you see, there are a lot of them, each with different properties. But it's important to understand fundamentals and basics, and if you work with system which supports some specific level of consistency, you would be able to just place it to compare it to other models and quickly research and understand. We have covered fundamentals of consistency models now, and I want just to say what we haven't covered. So there are a lot of topics which are closely related to distributed systems and to consistency if we look on the consistency from different aspects. And here is the list. You can see it, and I hope to cover them in future videos. They are all needed to understand the concept fully, without gaps. Here are the references. It's a literature which I used to prepare this video. And I remind you that there will be series of videos about distributed systems and software architecture. And my name is Ivan Fedyanin, and I'm very glad that you watched this video, and I hope it will be helpful. If you have any feedback, any questions or comments, don't hesitate to leave a comment and I'll do my best to answer it, or just I'll consider it when preparing my new videos. Thank you very much and bye!